welcome everyone to the stage. Win Cowger, the executive director at the Moore Institute for Plastic Pollution Research, and today he will be discussing uh, the updates to OpenSpeccy.
Thank you. Yeah. So in microplastic analysis, the main analytical data that we deal with very often is spectra, IR spectra, and Raman spectra are two of the main techniques that are employed. And typically we have hundreds of particles at least per sample. So that'll give us hundreds of these spectra. More common, I'm going to be talking also about hyperspectral imaging, which will typically be in the hundreds of thousands of spectra. Um, and this presents a real challenge because the traditional approach for analyzing these spectra is really one at a time manual exploration. When I first collected my first spectrum, I had some polyester fibers that I was trying to identify. This spectra was really bad, really poor signal noise ratio. And I asked my mentor, what do I do? How do I figure out what this is that I'm looking at? What types of fibers are these? And they gave me a book and they said, you're gonna need to read every line of this, every page of this book and figure out how to interpret it. And I just felt like that could not scale to the problem that I was trying to address for the microplastic methods that I was trying to develop. And there were some slightly better techniques that were available at that time. One of them was a automated spectral matching using a what's called a reference library. So you have a bunch of reference spectra that you have saved into a database, and you look for correlations between your unknown spectrum and your all of the different known spectra. And basically, the one that's most correlated, you could plot them together, and you could look for similarities or differences between the peaks and identify and determine whether you think that's the correct match or not. I do want to point out that there's been a lot of talk of developing AI techniques in the field, and in my opinion, this actually is already an AI technique. This is a k-nearest neighbors search where they're using a correlation as the distance matrix, and I think it's useful to start from that perspective and kind of think about where we go from there. So for k-nearest neighbors search, basically, this is just in two dimensions. So you have all your known material types, like maybe all the blue sample points are, polyethylene, and all of these are polypropylene, the red ones, and here's your unknown. In a k-nearest neighbor search, typically you're using Euclidean distance, so you would just use the distances that you could see there. For classical spectral library search, you're going to use a correlation. So you're actually going to weight things that are very far away by essentially the square of how far they are away. And you're going to give things that are far away a lot more importance in determining what your best match is. It's very interpretable. These types of approaches, they're really robust against edge cases. Um, some of the downsides, they're most sensitive to the largest peak because of that correlation. Because if the largest peak is not met in your unknown spectrum, basically you're going to get a penalty to the square of how different that peak is. And it can be pretty difficult to separate similar spectra. Giving the example, these are some overlaid spectra here. So you have HDPE, MDPE, LDPE. They all have very similar signals. So if you wanted to actually be able to identify the difference between these, it would be really hard with a k-nearest neighbors based search because it's basically going to see these as very similar, and it's just going to say they're almost perfectly matched. If you add a little bit of noise on top of this, you're like real environmental samples, you're going to have a very hard time differentiating these classes. And so this is where some more advanced machine learning, artificial intelligence techniques come in. I'm sure you'll hear a lot more advanced things than we're currently working with in OpenSpeccy. We do have a logistic regression, and which follows a similar type of idea to this. Basically, every single point in the spectrum gets its own weight. So you can say, for example, you feed that data into the machine learning algorithm, and it can figure out actually this small peak is the most important peak for differentiating the classes, and it will reweight that. So you see in this is from a paper where they essentially found this random forest regression showed, oh, this small peak is actually really important for this classification problem that they were doing. So the model is reweighting that and giving less weight to the big peak. These can be somewhat interpretable. For example, this feature importance ranking plots that you can make, these are pretty useful for interpretation. They can also maximize the class separability because they can pre-weight the importance of different peaks. But they're very prone to overfitting in a lot of cases, and that can be quite challenging to avoid, especially the more complicated the machine learning models start to get. In our lab, so we do have an accredited microplastic lab here in Long Beach, California, and we do a lot of high throughput analysis on our scanning FTIR machine, and we have a Nicolette IN10 MX, and we wanted to make sure that these automated techniques were working accurately. So what we did is we put homogeneous particles on the surface of stainless steel mesh. We did this for 20 different materials that we knew what we were putting on there. We could accurately determine what the shapes and sizes were as a spiking experiment to make sure that we're actually getting the right counts, sizes, types back. The OpenSpeccy automated workflow for this right now is basically what we do is we take this hyperspectral image, we create what we call a heat map, which is essentially the signal multiplied by the noise, and it'll allow you to pop out these where the particles are in the image. So you can see the visual image here. Hyperspectral image heat map corresponds to that. You set a threshold for how bright those particles, those pixels need to be considered particles, and then you can actually threshold out the particle regions. From there, we take the isolated particle regions and we calculate the average spectrum. So we just get down to one spectrum per particle. And then we run it through an identification algorithm. This drastically speeds up the k-nearest neighbors algorithm search because it is one of the most computationally expensive machine learning algorithms that you can use. And then we have a nice visual overlay that you can take a look at and make sure that it's working well. In hyperspectral imaging, you do have a lot of really nice additional data that you can use beyond just the class, the spectral information. There is spatial information there that you can use to actually improve your identification. So we do things like spatial smoothing across the hyperspectral image. You can do the particle compression algorithm that we mentioned, where we take the average of the spectra for each particle that we've identified. You can play around with if you have touching particles that have different types. You can play around with trying to separate those particles from one another. That's a whole topic in itself. And then you can measure the shapes and sizes of the particles based on the pixels. OpenSpeccy Online can do essentially all of this, especially for small hyperspectral images. It really doesn't struggle with anything smaller than maybe 1,000 to up to 10,000 pixels or 10,000 spectra. So you could already batch process your spectra or upload smaller hyperspectral images. For larger ones, we do have a OpenSpeccy R package. These are all open source free tools. And I do want to give a shout out to Zachary Steinmetz, who really helped to develop the OpenSpeccy R package. And with that, you can really automate whatever types of spectroscopy tasks you want. We're actually using OpenSpeccy in our lab to completely automate all of our lab analysis. So we're batch processing our hyperspectral images and linking that to all the other data that we're collecting in the lab. after we did this spike recovery experiment, we basically found that the accuracy and particle count that we were getting was about 86%. The identification accuracy for material type was 90%. Size accuracy, we had a little bit of an underestimation on the particle sizes. And we were able to really analyze a whole 100,000 spectral map in under a minute with a typical laptop computer. So we felt like that was a good threshold to meet. Actually, so as an accredited lab, we're required to meet certain standards for our recovery rates, so these accuracy percentages, but also the uncertainty. So the our relative standard deviation needs to be below 40%. So we were able to meet those requirements that we have as an accredited lab. Across all the different metrics. And so this is great. We feel like we've met the accredited standard for this, but I do feel like we really need to proceed cautiously. Some big issues that we've noticed with these types of approaches, especially the automated ones, you can have particles moving in between the time when the visual image is collected and the hyperspectral image is collected. And then you end up getting images like this, where you see these particles are kind of not overlaying the particles in the visual image. You can also have poor signal near the edges of the particles. Touching particles are going to get merged into one. Um, and you can have artificial particles being created due to the poor signals near the edges of the particles if you're not careful. So there's a lot of little tuning parameters that I mentioned earlier that you want to take a very careful look at and make sure that's working well. Likely do one of these recovery experiments in your lab to be able to make sure you're actually hitting, accuracies and uncertainties that you would be confident in. An inappropriate background. The background is one of the most critical things. It needs to be very flat and it should likely be made of metal or something very transparent to your process. And in this case, we were using metal, but the metal that we were using was too rough. And basically, what ended up happening is the metal had these holes in it for the pores, and the pores were 20 microns, and the step size of the hyperspectral image was 25 microns. So we were getting a lot of roughness from that. And it started thinking that there were particles in the pores, basically, even though there weren't. Also, you can see here there's this region where it doesn't think that there are particles in the pores, and that's due to it being out of focus. So if you don't have it being perfectly flat, you can get, even across one hyperspectral image, you can get some issues with the end result there. We did this study with Sebastian Primka to understand OpenSpecky's limitations back in 2024. OpenSpecky and many other spectroscopy software use ATR spectra for their reference library. It's a very reproducible spectrum that you can collect. It's really, really rich spectral information. But it comes with a challenge because a lot of times we're not actually using ATR data. So we'll collect reflectance data or transmission data, and then we'll try to match it to these ATR libraries, and you can end up getting a accuracy hit from that, a substantial one. So this is out of the box accuracy. This is kind of like a worst case scenario for these different spectral collection modes. And ATR was, the best at the time because we had a lot of ATR reference spectra in the library. But now we've added in these reflectance spectra and the transmission spectra, so it's getting a lot better. Some types of particles can be very challenging or even impossible to collect good spectra of. Tire wear particles are definitely one of those that for infrared spectroscopy, I consider them mostly one of the most challenging, and for most of the spectral collection strategies, they're going to be impossible. Um, They have very poor signal, high noise, also really thick particles. It doesn't matter as much for ATR spectra, but very thick particles will end up having oversaturation of the peaks. And so you can see that here. Just in developing these reference libraries in general, microplastics don't just have a single signal. Unfortunately, they have a lot of different signals. Even a single particle throughout its lifetime, when it starts aging, the signal will change due to the aging that's happening and it's changing its chemistry. Um, you need to have a diverse suite of weathered particles, which we do have in OpenSpeccy in the library. Mineral doped plastic has a very strong infrared signal. So the SIO peak is very strong. And these correlation-based searches are going to be super biased against that big peak and say, that's the only thing I care about, essentially, and not actually see that the plastic peaks are also there. Natural and synthetic polyamides are very similar, and a lot of times these end up resulting in both false negatives and false positives. So in overview, contemporary spectroscopy techniques are employing k-nearest neighbor search with a correlation as the distance metric. More robust models can definitely improve the class separation, but are more difficult to interpret and prone to overfitting. Hyperspectral imaging can accurately measure count, type, and size, but I definitely recommend you verifying that on your machine with your settings because they could not be working very well if you don't have everything perfectly tuned. It took us a long time to get it tuned for our setup. Um, Issues can still persist, and it requires a high level of expertise and careful consideration to avoid and resolve. So that's all for me. Thank you.